talk about stress concentrations and a little bit of SolidWorks finite element analysis and how it relates to those stress concentrations. Basically, we'll do some calculations by hand, and then we'll do the same calculations but using SolidWorks simulation to see if they match up or if they compare. So what we're talking about is the idea that if you were to have a part that you've made, so maybe we make a part like this. Let's actually draw it with straight lines instead of just random lines. So I've got a part, it's got some width here, but then it has to get smaller, maybe like this, and go down to some more narrow width, something like this. So when you build this part, this transition between the narrow part and the wider part, there'll be a stress concentration right here. You could kind of think of what are called stress flow lines, and you might draw them something like this. You know, something like this. This is just a, whoops, missed the corner there. A graphical representation of how the stress has to flow in this object. And what you notice is that here in this transition, they kind of squeeze together. And so this squeezing together creates stress concentrations at these transitions. And the sharper this transition is, the more these stress concentrations will have to, you know, they'll have to make a tighter, not loop, but path around this corner. Now, if I had this corner much more rounded, then this transition from here to here, it could be more gradual, you know, versus having to step up and over really quickly. So sharper corners create higher stress concentrations. And a lot of times you deal with this by coming in here and rounding this corner over. This is called a fillet. When you make that sharp transition more rounded, that's called creating a fillet there. And so the radius of this fillet greatly influences the idea of how much stress is concentrated at this corner, or any kind of transition. These things are very important for brittle materials. So brittle materials meaning they don't stretch a lot before they just break. If we were to draw a stress strain diagram for a brittle material, well, let's draw the one that we've been drawing before. So sigma and strain over here. And we've been drawing stuff that looks like this, right? Where, and again, I am exaggerating the slope here. These are usually much more steep, but I'm exaggerating it. There's a linear region, and then there's this really large plastic region where things are stretching out. So this is for a ductile material. So ductile materials are a little bit able to take on some of that stress and reshape themselves. So, you know, yield, but reshape themselves to kind of deal with the stress concentrations a little bit. So you might see a little bit of local yielding in this corner from it stretching. And when it does that reforming, that stretching, it will do what's called strain hardening. Remember, strain is some kind of change in shape. In this case, maybe a change in length. And when a material does that, it gets a little bit harder. When a ductile material stretches, it has strain hardening. A brittle material, this same kind of stress strain plot is going to look a lot like this. You know, there's very little of the yielding section. It just strain, or well, you apply the load, and the stress and strain is pretty much linear, and then it breaks. You know, there's very little amount of ability to yield. So like glass or something like that, where you can't really stretch it very much at all. If you change its shape at all, you've pretty much broken it. So this would be a brittle material. Oops, left out the L. There we go. So this idea of calculating these stress concentrations is very important for brittle materials because they can't really easily deform and strain harden and adjust their own selves. You can't ignore it for ductile materials. It's just not as immediately important. It will matter if this is a fatigue situation. So fatigue means that you load and maybe you unload and load again. So you stretch and release, stretch and release. Or maybe you just stretch more, stretch less, stretch more. It's some kind of cycle of loading. So those kind of situations, even for ductile materials, these stress concentrations play a big role. And it is a stress concentration. Sometimes you call them stress risers. So in the idea that they raise the stress. So what we're going to do is calculate a multiplier, basically, the stress concentration factor, and multiply the stress that we would normally calculate the way we've been doing it by the stress concentration factor and raise the maximum stress to this new level. And so sometimes they're called stress risers. So maybe you're at pretty close to your factor of safety without considering the stress risers, and then when you do consider them, maybe you have exceeded your factor of safety as far as stress goes. So let's set up an example, calculate it by hand, and then let's go over to SolidWorks and see how SolidWorks would do the same thing. All right, so let's use that example with the tab, a wide area that goes down to a smaller area. So let's see, I'm trying to find a pen that's going to write well. They're all kind of starting to fade on me. That one's working. So here's the wider area. And then we're going to narrow it down, I don't know, something like that. We will put a fillet in here this time, so it's going to have some amount of curve right there. We'll have to define what that actually is, though. I can't see what I'm drawing. All right, and to load this thing, what we're going to do is put an axial load right through here. And let's say that it is 2,000 pounds. And then we would also need 2,000 pounds over here for it to be in equilibrium. We need some dimensions on this thing. We need to know how big it is. So let's say these lengths don't matter too much. Obviously, if you make them too short, then that would create new issues. But let's just make them, 2 inches long, so it's not really affecting our overall performance here. So we'll make those each 2 inches long. Like that. And then we need to know the radius of this fillet. We'll make them both the same, even though I kind of drew them a little bit weird looking. We'll make them have a radius of 0.08 inches. That'll be our radius. Now we need this width, and then we also need to know how thick it is into the paper. So let's just say that the thickness is 0.1 inches, so relatively thin, 1/10 of an inch. 1/10 of an inch would be kind of right there, that thick, right in there. And we need to know these widths here, so I don't have a good place to put them. Let's put them over here. We'll pull it out further so that it's not exactly overlapping that. I don't have enough room though. Let's make this width 2 inches, and then let's make this one, that looks like maybe a 1/2 inch. I don't like doing this, but we'll put it this way. All right. Now, if this is our situation, we got this little metal plate. It doesn't particularly matter what metal it's made of, although we do have the issue where if it's a brittle material, this stress concentration is going to be more important. Although when we simulate it, it'll be a ductile material, a steel of some sort. But calculating the stress doesn't change depending on what material it is. It only is what actually happens changes depending on the material. So what we've got is we find the place where we already know the stress is worse. So that's going to be in the thinner section over here. So we would come in this thinner section and, you know, create a little free body diagram of that section. And I'll go ahead and cut it open. I mean, we can tell that there's 2,000 pounds inside it, but we just want to be thorough. So let's pretend we're cutting this section open and drawing kind of a three-dimensional free body diagram. I don't normally do that, but this time we will. So something like this. Forgot which one to use that one. All right. So here's our little cut open piece. This green line is this surface. So this is the surface where the stress exists. And we're going to calculate the stress that we calculated way back in the very beginning of this course, you know, the force over area kind of stress. So we're going to assume that this 2,000 pounds is this one, and this is the internal stress or internal force that's causing the internal stress that we're interested in. Right? And we already have all these dimensions here. This is the thickness that I just noted up here, 0.01 inches. And this is the width or the height, whichever you want to call it here, and I called that 0.5 inches. And we could go in and calculate the stress on this surface, so the internal stress right here. So the internal force is 2,000 pounds. The area that this 2,000 pounds acts on is 0.1 inch times 0.5 inches. And that will give us our stress, the average stress, the one that we've been calculating. So 2,000 divided by 0.1 and divided by 0.5. 40,000, actually that's too much already, isn't it? We're going to need a strong material for 40,000 psi of tensile stress. In fact, why don't we look at our materials that we have available here. Let's get one of our charts up. And just get one real quick. Well, as quickly as I can anyway. It's taken a while. All right, almost there. I guess I can go ahead and let you look at it. Material properties. All right, so we need something with a elastic strength of at least 40,000 psi. So maybe this 0.2% carbon hardened steel, it has 62,000 ksi. So that would work for us. It's a ductile material, although it is hardened, so that makes it less ductile. And it's 62 ksi. Well, it's not, it has the same modulus of elasticity as these others, so it's not particularly brittle any more than these other materials are. Now, but look at the some of these other materials have a little bit more, although you can't really tell just from the modulus of elasticity. you can tell that there's a difference between the elastic strength and the ultimate strength, 30 KSI, whereas wrought iron is on the brittle side, and there's not as big a difference between the elastic and ultimate strengths. All right, anyway, that one would work. 0.2% carbon hardened steel. Has actually all of these would work. All right, so we know that much anyway. Let's get all these things off of my screen. There we go. So that is the stress basically in, let's see, how do I want to show this? In this region. Now, this region over here, if there really is a point load, there's some higher stresses in right near that point load. We really treated this more like a distributed load. Maybe I should have drawn it more like this. So we treated it more like this, right? We haven't really worried about that in the past. We've just kind of, these point loads, we automatically assume they're distributed evenly across the whole surface. But if there really was a point load at a single point or a small area right here, then that little area would have a higher stress than everything else. That's not actually the stress concentration we're talking about right now, though. And as we get closer to this transition from, even though we're going from a small to a larger area, it's still a transition, and we need to take this stress and we're going to have to multiply it by some amount. So how you figure out the amount to multiply by is you need a chart like this one. And these are all over the internet, in books, all over different places. And there are many different ones. Like here's another chart, same idea, except this one's for torsion. We'll do something like this in a minute. But this one is basically the same shape that we have, wider, narrower, flat piece with axial tensile loads on it. That's more or less what this is. Whereas this one is round, big to little, but round, and torsion loads applied to it, torques. So you have to find the matching chart, first of all, so that would be this. And then most of these charts have multiple traces on them, and an X and a Y axis. So to figure out which line we need to work with, you look over here. On most of the charts, it's somewhere on the chart it tells you how to determine which trace. So this one is right here. It says that you take and divide capital H divided by lowercase h. So you don't know what those mean, and they're written on the diagram. So in our case, h over h equals the wider distance, 2 inches, over lowercase h, the smaller distance, 1/2 inch. All right, now I can already see a little bit of a problem here. We should have made some different numbers, but that's okay. We'll figure out what to do with it. Oh, I did 2 divided by 0.5. 2 divided by 0.5, not 0.05. 4, so that's 4. Now, our chart has numbers like 1.01, 1.5, 2, and it has one for 3 that kind of only exists over here. So we don't have one when the ratio of how wide this is to how narrow this is 4. So this chart is only going to help us so much. So there's such a difference between these two distances that we might have some problems. But what we'll do is we'll take the line for 2 and we'll realize that we would actually need to be up above that. But this particular chart doesn't give us data for a 4. It gives part of a data line for 3. These charts are sometimes they're empirically driven, just data sets that are averaged out and plotted, these trend lines. Sometimes there are theoretical backups behind them, so they come from different sources, and I don't actually know how this one, it doesn't say. Well, I guess we could go look at the reference over here, 1981 Collins, and see if it's an empirical or theoretical chart or whatever. It's probably, most of them are probably empirical. But we have this little section of a line that has h over h of 3. We need one that's even higher than that. But you can kind of see they're getting closer and closer together. So there's probably not a lot of difference between 2 and numbers greater than 2. So we'll say that we're working close to the line for the h over h of 2, which is this line. And realize that we're only close to that line. We're actually probably a little bit above that. We don't have a good way to extrapolate, though. We can see that the difference between 2 and 3 is not a lot, so 4 is probably just a little bit more above that. So maybe we'll be a little bit above the 2 line. So we'll have to do a little bit of approximating. The x-axis has a scale, and it is shown to be r over h. So r, we have to look up here, r is the radius of the fillet, h is the thickness of the thinner section. So for us, r over h equals r, we're assuming both of these have the same radius, 0.08 inches. These were inches, the inches cancel out. You do have to make sure they're in the same units, otherwise your units don't work out. So you do have to convert them both to inches, both to millimeters, or whatever they are. This is 0.08 inches. H is the same as it was before, 0.5 inches. Again, the inches cancel out. And let's see what we have. 0.08 divided by 0.5 is going to give us 0.16. So we have a 0.15, 6, 7, 8, 9, 10. So this line is the 0.16 line. So we can use that, and it's going to intersect underneath the picture here. We'll have to deal with that. So we're on that line, and we're on a curve that is coming in. That's where more or less the 3 line would come in, and we think 4 is a little bit. We're looking at somewhere in that point, having to guess a little bit. So most times when you're in an academic setting, what they do is these things line up on, like, something would line up at a point right here, or something that where it's really easy to figure out. So we're having to stretch this chart a little bit beyond what an academic setting would normally do with it. All right, and then what you do is we just find that point of intersection, which we think is more or less, if I were to draw the H4 line, something like this. So we're having to do a little guessing. We take that intersecting point, and come over here, and we read there's 2.0, right in the middle would be 2.1. We're a little bit more than halfway between 2.0 and 2.1, so we might call this point 2.0, a little bit more than halfway, maybe we'll call it 6. You could, with a more detailed chart, or even one that actually had a h over h equals 4 line on it, you could maybe interpolate or whatever to get a better guess here. We're guessing on this digit. Or you could do the traditional thing where you just guess to the nearest half and make this 2.1 if you wanted to be a little more conservative. All right, or conservative in this case. So we take this number, 2.06, and the stress that we calculated through our regular process, and you multiply them. So what this says is that sigma max at the corner in here, so here or here, they're the same, is equal to K. K is the stress concentration factor that we just figured out, the 2.06, times sigma, the stress that we calculated from our average stress equation. Maybe in fact we'll do average on here. And so we would end up with 2.06 times 40,000, or 40 KSI, and that's going to be 80, 2.06 times 40 is 82.4 KSI. And what that says is that even if we use that steel that we had picked out, the 0.2% carbon hardened steel with a 62 KSI tensile strength, which looked okay before, I can't get it on the screen, but it looked okay before 40,000. We had some factor of safety, but this is saying that, you know, at this corner we actually have 80,000 KSI of stress, which is not okay. We'd have to go up to some of these stainless materials down here, or the heat treated steel, you know, something in this range to be okay. So that's one reason this can affect your designs, even for a ductile material, is if you're kind of close to the limit, calculating with the, you know, the traditional average stresses, then you go and throw one of these stress concentrations on there, you might have exceeded the yield strength. Now, I'm not sure what SolidWorks is going to do with this, because it will exceed the yield strength, but let's throw it in SolidWorks and set this up and see how it responds. So let's get SolidWorks showing. There, no, that's not SolidWorks. There's SolidWorks. We need a new part. And it's, well, let's go to model the part first. Basically, it's just a rectangle and another rectangle. And we had this one at, oh, I gotta look at the pic. I think it was 2 inches. Let me get it back. Yes, 2 inches. We are already in inches, all right. We had this one at 0.5 inches. We had this at 2 inches. We had this at 2 inches. We did have it centered, so this distance we would have at, let's see, what would that be? Well, it would be, we could calculate it, right? 2 minus 0.5 would be the leftover, and divide that by 2. 0.75. All right. We could check that with this dimension, right? And it is 0.75. Now, if I place, oh, well, let's do it. If I place this dimension, I get this pop-up that says make this dimension driven or leave it as driving. What that's talking about is, I'm going to leave it off of there. If I do dimension this, I've already put over here that it's 2 inches wide, and then here and here I have put enough information that you should be able to calculate this. It only has one value left, so SolidWorks doesn't leave room for any tolerances or anything when we're doing it this way. So there's only one number, 0.75, that can go in here. So in order to place this, it says you can make it driven, meaning that you can't set this one. It would just equal whatever the remainder is. So it'll equal the remainder of 2 minus these two dimensions. So if I change either of them, then this one will automatically change also. But I can't change this one to make these other two change. And this is pretty standard. Oh, let me. Oh, I want to delete it. Well, delete. There we go. Even if you're drawing these and sending them to a machine shop, you normally don't want to over constrain the dimensions. You know, if you have 2 here, 0.75, 0.5 here, and 0.75 here, there's no room for error on any of those dimensions. So normally what you do is you find the spot where it's okay to have error and leave that one open, so the machinist has one section where they know all this error can stack up on that end and not affect your design. And you would also have tolerances on all of these, you know, 0.75 plus or minus whatever. We need to erase this little line, so let's trim that. And we need to put our fillets in. So here's a fillet on that corner and that corner, and we made them in our design 0.08 inches. So they're kind of small. There's our shape, and then we need to extrude it. I made it 0.1 inches thick, which it's already set at. So it's a pretty thin little piece of sheet metal-ish type. I don't know if you'd count it as plate, but it's pretty thick sheet metal. And let's go to simulate this thing. So simulation, we're going to do a new study, and it's going to be static. We don't want fatigue or anything like that. It's just going to be pulling on it. And we need some material, so let's edit now. Let's see if we can find a stainless steel material. Well, it kind of hung up on me. Not sure. It's thinking. Not sure why. There we go. All right. Here's an annealed stainless steel bar. Let's see what kind of strength it has. It's 80 KSI. That's close. Let's see if we can find something a little bit, maybe a 321. There we go. So we'll use this 321 annealed stainless steel, which has a tensile strength of 90 KSI. And we had it, our stress concentration factor said that we were going to need about 82 KSI. So let's apply that. This looks like it'll work. We need some fixtures. So, well, or I didn't want to do it that way. Back here, we need to apply a fixed geometry. We'll just make it as everything fixed on this surface so that just doesn't move at all. And then we will, not sure why I'm locked into rotating this way. I've got something going weird, a little bit strange. All right, we'll apply a force on this end. So external load, force, it's going to be a force on here. Now this is showing a compressive force, so let's reverse the direction so it's actually stretching it. Change our units to English, and we put 2,000 pounds. Oh. Okay, so that's all it takes to actually set this thing with constraints and forces and a material. Now let's mesh it. Let's just take the default settings for this. So let's just mesh it and run and see what happens. All right. Hey, I'm back to rotating the way I wanted to. I'm not sure what I had locked in. All right, so that looks like what we expect. I also notice this top is not flat anymore. It is kind of concave. That's showing that if you think about conservation of mass, and I made this section, or actually the whole thing, longer. You can kind of see the original end was right here, the original end right here. And so I made it longer, so that means that somewhere it had to get smaller. If I made one dimension larger, I had to make another dimension smaller. And so you can kind of see that SolidWorks is simulating that. You can also see in this corner, that's where our maximum stress is. Now it's in newtons per meter squared, so let's change that over to KSI. So we want KSI. I also want it to be in floating point. 3 decimals is fine. Look at that, 82.3 KSI. You can kind of see it right down there. We predicted 82.4 KSI. So that is what I would call a model that agrees. Normally they aren't necessarily that close to agreeing, but this one actually is. And you can check other things in here, like maybe we want to see what the mesh looks like. So we could go over here on mesh, and we could look at the details, and it's got 9,300 elements. It kind of gives you some of the sizes of these elements. We can actually view it. Where do we view it? Show mesh. So there are all the little triangles. Actually, not triangles. They're three-dimensional. You can kind of get an idea of their shape. Well, that's, I guess that corner piece right there kind of gives you an idea of these little pyramid shape-ish, or not pyramids, they're tetrahedrons, I guess. So you can kind of get an idea of what the mesh looks like. So what's happening here is every one of these little volumes gets its own set of calculations based on all of its neighbors. So you have to have some where you know the conditions. Like on here, we know the force is applied to this surface. And over here, we know that all of these surfaces are fixed in place. And so if you have those boundary conditions, then it can start to work out, well, if this one experiences that, then its neighbor is going to experience this, and its neighbor is going to experience this. And so it creates this giant matrices behind the scenes of how all of these mesh elements interact with one another. And so we could have more or less elements. We have the default, if we went in and did create mesh, we're kind of, we're on the little bit on the higher side of this slider. Now this is just one way you can modify the mesh. Like we could go in and make it very coarse, and they're much bigger, right? We can run the simulation here, and we get a different 72.37 KSI, where the other one predicted 82 KSI. So the number of elements you use will affect your simulation. But you don't necessarily want to just go here and, well, just max this thing out and that'll be best. You don't necessarily want to do that. For one, it takes longer, not that long, but obviously much smaller elements. Let's run that steady. Takes a little bit longer. Again, these aren't particularly complicated. Even with the number of elements here, it's still not that complicated. And we get another number, 89 KSI. So what you really want to do is you want to do some kind of theoretical work like we did on paper, so you have an idea of what you're looking for, and then do some multiple simulations where you do a coarse mesh and a medium mesh and a high density mesh and maybe some in between there, and you look at how does this maximum stress, how does it change as you increase the mesh size. You should be able to see some kind of convergence to the number that you would expect. You can do other things like we could go in here and apply some mesh controls. So maybe we know that on this little surface right here, let's just do the whole surface, we want to have more detail there. In fact, let's delete the edge and just use the surface. And we want to have on that part a very fine mesh. Because this is where we expect the maximum stress to be. So we create a denser mesh right there, and you can kind of see how we were already on a dense mesh, but it goes in and puts even smaller elements in that one place that we're interested in. And so maybe you can make a coarse mesh everywhere else and then a fine density mesh where you're really interested in. Notice it's also taking a little bit longer to solve, and we're still on a pretty simple model. And we get the 89 number again. Let's go back and make most of it a medium density mesh, and we still maintain that mesh control here. Now actually we probably should put it over here. I didn't actually check, it might be picking up the maximum stress on this side. So let's add another mesh control on for some reason that one, there we go. Oh, I didn't actually do it though. Delete that one. I didn't create the mesh. Apply mesh control to this surface. We're going to max it out and create the little mesh there. Now we've got those two corners. You kind of see how there's more, a higher density of elements in those corners. And let's see what we get for a study now. Now we're at 90 KSI. So you can kind of see that you can't just automatically take the numbers from a simulation. You have to have some idea what you're looking for to begin with, because we've got numbers everywhere from 70 KSI to 90 KSI, 72 or whatever. We calculated 80 KSI, so we're at least know we're in the ballpark, and that gets you started on, all right, now what do I need to do to investigate where it's right. We also got that 82 from this chart. Well, no, not that chart. This chart where we, kind of guessed a little bit. So, but you're in the ballpark. So that's kind of the idea there. Let's do one more with the torsion just to show how it would work. So something here where we have round bars. There's a torsion. This particular one, and the other one did too. They don't all have this, but some have the average stress equation shown on the chart. This one also does. It actually has TC over J, and then it has put certain variables in specific to these variables that are shown on the chart here. So it's just this equation is specific to these variables. So let's not draw another one. Let's just say that we have torque of, I don't know, 50 foot-pounds. And this would also need to be 50 foot-pounds. And let's say that this diameter here is D, smaller diameter is 3/4 of an inch. Let's make the larger diameter 1 inch. And let's make this radius something that would work with that. Let's make it 0.1 inches. All right. Now I didn't check on here. We have even only 3 traces here, so we have even fewer options. D over D. So D over D, we have 1 over 0.75. So if we do that math, 1 divided by 1.7, or 1 divided by 0.75 rather. 1.3, we have a 1.2. Okay, so we're between the 1.2 and the 2 line. We're closer to the 1.2 line. And then our x-axis is R over D. So R, we have 0.1 over 0.75. Whoops. 0.1 divided by 0.75. 0.133. So we have a 0.1. It looks like this is 0.2. So these are counting by 0.11, 0.12, 0.13, 0.133 is going to be right in there. So where'd our ruler go? So we're on that line, and we are between these two, but we're closer to the bottom one. So we're going to guess right there. We could do some actual, we have 2 data points here. We could actually interpolate those. We're just going to interpolate with the graph right now by hand. So here's 1.2, there's 1.3. We're a little bit past 1.25. Let's say 1.26. I like the 6, I guess. I don't know. Or you could just call it 1.25. All right, so 1.26 is our multiplier. So it's not as large as the last one. Our calculation, we can use this one, 16t. So the 16 is coming, it's basically using j is pi over 2 times c to the 4th. C is d over 2. And so it's built all of that in and just kind of simplified it for you there. But you could certainly go back to just tc over j and do all that manually. So tau equals 16 times torque of 50 foot-pounds. I need to convert those into inch-pounds, so 12 inches per foot. Divided by pi times d cubed, so it has d as this diameter. For us, that's 0.75 inches. And we have to cube that. So our base torque, 16, or average torque, times 50 times 12, divided by pi, divided by 0.75 cubed, 7,000. So our average stress is 7,243.3 psi. And then our multiplier is 1.26, so tau max, kind of running out of room here. Tau max equals the 1.26 number times the average stress. So 9,126.6 psi. Now this is a shear stress, so we would have to compare that to shear strength, which is, you know, half-ish of the tensile strength. So we are getting kind of close to a dangerous area for your average steel, because it's going to have a tensile strength in the 18-ish, well, 16 to 18 ksi, somewhere in there, and we're at, you know, close to 10 ksi. So we're not super dangerous, but we're getting close. We could simulate this in SolidWorks. When the difference would be, we'd have to model this guy, and when we do an external load, you can do torques. You can apply torques, and so let's see what time it. Yeah, why don't we try doing that? So let's go file, new, part. Okay. So this one we need to make some cylinders. Let's do a revolved base for this one on the front plane. We'll come off this center line and basically do this guy, right? And then this would be the radius of the thinner part, which we had as a 0.75, so it's 0.75 divided by 2. And this one we had as 1, so this is just 0.5. These links, we just make something reasonable, 2 and 2. Oh, I didn't think about it. We may not can fit our fillet in here. We called this a 0.1 inch fillet, but Yeah, it'll fit. It's just barely. You can't make much larger fillet than that. And then we will revolve it all around. 360 degrees. The axis of revolution will just be that line. And there's our little part. That looks like what we expect it to look like. Normally we would save it here. We'll just go straight into a new study. Static. We'll apply some material. For some reason, the material selection is really slow right now. I don't know why that's being so slow. So let's just do one of the plain carbon steel materials. Fixtures, we'll fix this end over here. So fixed geometry on this end. And then we'll apply a torque on this surface over here. Have to remember how you apply torque. So this one is, the face will be this, and this is the axis. We can select that as the axis, and that looks like a torque. But we want a 50 foot-pound. I'm in inch-pounds, so 50 times 12 inch-pound. And now we've got a torque on there, and we can mesh and run. Oh wow, it did some weirdness out there. That's really strange. Well, it is exaggerated by 250 times. So sometimes you get some odd things. Here is where we expect our maximum stress. It's in Pascal, so let's change it over to KSI. We did KSI. No, we did PSI. Let's do PSI and then make it a floating point number. We've got quite a bit different here. Our calculation said 9 KSI, and this is saying 15, 16 KSI. So it's not like orders of magnitude larger, but it is giving us quite a bit larger stress here. So I've never actually done one that created this kind of particular shape when we did the torque. It might be better to put an opposing torque over here instead of just fixing this surface. When we simulate it, I haven't done a whole lot of these torques. I just wanted to see what it would look like. And let's see what mesh we ended up with. Relatively normal mesh, but you might want to use a different type of element for the torque here versus these tetrahedrons. I don't know what my choices are, if I even have choices. Let's see. All I have is apply mesh control and create mesh in here. Oh, we could do a curvature based mesh. That might help us out. I can specify some of the sizes. What's in here? Let's see if we get a little bit better. No, it actually even is further away from what we calculated. I guess we should actually calculate to make sure I did the calculations right. That's always possible that I did the hand calculations wrong. These charts, I think I mentioned, are always either, some of them are empirical based, some of them are theoretical based. Oh, my phone's ringing. Turn that off. All right. 16 times 50 times 12 divided by pi and divided by the smaller diameter cubed. No, that's right. And then, yeah. So we just have some disagreement between our hand calculations and the simulation. Doesn't mean either one is the one we should follow. We should investigate, why is our simulation doing this? Why is our, or we do have any errors in, maybe we looked at the chart wrong when we picked out some of these points here. So you usually balance between the two of them. You do by hand to get an idea of where you should be. Then you look at the simulation and like, well, is there something about the simulation that's inherently wrong? This is why you don't just automatically trust that a simulation is giving you the correct numbers. There are a lot of little details that the default settings in something like the SolidWorks simulation are good most of the time, but maybe they don't apply under certain conditions. Maybe they don't apply when you are doing a torsional analysis. Maybe there's another setting you need to look at. And so you're not terribly far off between these two, but there is enough difference between them that you probably would want to go in and track down why are they different. Is there something you're missing over here in the theoretical solution, or is there something that is in the simulation that doesn't work the way you're expecting it to work? All right, this is actually the last of these in this series for statics and mechanics. And next time probably well, there won't be another video in this particular series. I think the next video series I'm doing is actually on measurements, so basic measurements, and that won't start until September or sometime. But this should finish off this little package of basic introduction to statics and mechanics of materials. Some of the things are a little beyond basic, some of this finite element stuff is a little beyond just the basic intro things, but this is actually the last one of them, and we will wrap it up here, and I'll keep adding videos, but not necessarily to this particular series of stuff. Maybe some example problems here and there, but this one's probably closed out, and we'll move on to something new. So I'll see you in the next thing.